Okay, so let's do in class 10. It says show the vector field is conservative, then calculate the work done on an object moving along a curve from 1, 0, 0 to 3, 2, 4. And here's our vector field right here. So for the vector field to be conservative, the I component must be the partial derivative of some small f with respect to x. The j component must be partial derivative of some small f with respect to y. And k must be partial derivative of small f with respect to z. In general, most vector fields will not be conservative, so just special type of conservative fields. So we're basically looking for a small f whose gradient is big F. So you can think of this small f as like the parent function for big F here. Okay, so let's find the small f. So we're going to integrate this guy with respect to x to find the small f. So let's do that first. So doing that, I'll have my small f will then be integral of fx with respect to x. So then be integrating this guy is my I component. So the first guy doesn't have any x, so it's just going to be just x, y, e to the z squared y. Then integrating 8x would be x squared over 2. So the 2 will cross off there will be 4 x squared y. This become 9. This is like a constant here, so it'll be 9, say xz, plus 5x plus some constant. But the constant here will be a function of both y and z because we're treating y and z like constants. So my constant here is actually a function, can be any function of y and z. Okay, let's do the same thing now for, well, I'm going to skip actually fy for the time being because the integral there is going to be harder. Let's do this one first. So let's integrate it, this guy. Okay, so integrating this guy, we'll have, so integrating our f subscript z with respect to z will be make our f also. So I'm going to integrate the k component over here. Now I broke it into two pieces because the first one's going to require a u substitution here. So I'm going to say let u equal the z squared y. So then du dz will be 2zy. So then du will be 2zy times dz. So then dz will be du over 2zy. Okay, so bring it over here then, this whole thing, this will equal so it'll be equals 2x y squared z e to the u times dz, which is du over 2zy, here. And then we have the integral of this guy over here beside it. Let's integrate that. So integrating 3z squared with respect to z will be z cubed. And integrating 9x will be 9xz. And it's going to be, I'll erase this now. It's going to be then a plus a constant here. The constant now will be a function of x and z. Okay, so let's keep going. Okay, so the 2zy cross up 2z and a y there. So just xy and integrating eu, so it's going to be xy e to the u. But u here is z squared y. That will be plus z cubed plus 9xz plus our constant, which is a function of x and z. Okay, so let's keep going. Let me erase some things here. Okay, so summarizing, we have this. We have f obtained two ways by integrating the fx guy and integrating the fz guy. So they must correspond. We'll come back to that in a second. But now let's find f by integrating the fy guy. So let's do that. So integrating our fy guy, we'll have this. So I'm integrating this guy here. I broke it into two pieces. So I'm integrating that first piece, then integrating that. You'll see why, because this first piece is going to require integration by parts. So let's recall integration by parts. So here's the integration by parts formula. We're going to apply it to this circle piece here. So I'm going to let the u be this guy here. So let u be the x plus x, y, z squared. And let this part here be the dv. So doing that then, du, dy will be 2, so that'll be 0, it's going to be 2xz. Sorry, I messed up there. It's with respect to y, so it's going to be x z squared. So then du be x z squared times dy, and our v over here will be integral of e to the z squared y dy, and you can make like a w substitution. Let the z squared y be the w, and go through it. I'll let you check, but if you go through that, you'll just end up with 1 over z squared e to the z squared y. Okay, so let's keep going. You can double check that this is the integral, because if you took derivative, here, the z squares would cancel. Okay, so let's keep going. So making the substitutions into our integration of parts, then we'll have our u times v. So it'll be u, this guy, which right here, it's my u, times my v, v is this guy here, which I have right here, then minus v, which is here, times du, which is the x z squared guy. So we got this. Okay, so notice here the z squares will cancel there. Okay, let's keep going. So integrating this last guy will be here. It'll be x e z squared y. When you integrate e to the z squared y, it'll be 1 over z squared again, so it'll be this. So this guy will go to here. Okay, and you can notice here actually that if I multiply this in, this guy will cross off with that one. So it'd end up with then just, and the z squared cancel here, so just end up with x, y, e to the z squared y. That's the equal to the circle piece here. So we still have to integrate this one now. So let me erase this now and make that substitution. So by integration of parts, then the circle piece becomes this. So we still have to integrate this guy, so it's going to be then plus, integrating respect to y, so it'll be 4 x squared y, minus integrating that will be y squared. Now plus the constant here would be a function of x and z. Okay, so now let's compare all three that we have. Let me write all three together now. So here's all three written together. So I actually noticed when I wrote this, I just wrote this one last time. There should be, since integrating with respect to z, it should be x and y here. Okay, so we need to make now all these three equations agree. So notice they all have the e's in them. That's fine. And I'll start trying to match them up. Well, this one has the 4x squared y, so does this one. This one's missing it, so I'm going to add it here. 4 x squared y. I can do that because that's a function of x and y. Okay, this one has a 9xz, so does this one. This one's missing it, so I can add it here. 9xz. I can do that because I can add a function of x and z, so that's fine. Then we need 5x, so 5x is missing from this one. I can add it here. It's missing from this one too. I can add it here because it's a function of x in both of them. So that's taken care of. Okay, so let's keep going. Okay, the second equation has z cubed. The first one doesn't have a z cubed, but I can add it there because it's a function of z cubed. And I'm just left with the minus y squared now. I can add that to this one and up here. Okay, so it looks like we're able to do it. So summarizing, so hence, so I'm going to write down our final f here. So writing down my final f, I get this. So at any point, if this had it broken down, it would not be conservative. But here you see it didn't break down. We're able to find a solution. So therefore, our vector field is conservative. Okay, now let's do the line integral. So to find a line integral from 1, 0, 0 to 3, 2, 4. It doesn't tell us the path. So it could be any path in here, just starting here, ending here. But it doesn't matter what the path is. All that matters is the starting and ending point because we've shown it's conservative. So by theorem 14 then, when it's conservative, once you find a small f, which we've done, it's going to be basically small f of ending point minus small f of beginning point. So here's my small f up here. So you're going to put, this would be your x, y, and z, and same over there. Just plug it in there and evaluate. So I'll let you check when you plug those in. So when you plug those values in and work it out, you'll end up with this as your final answer. Okay, so we're done.